Okay, guys, I think I'm going to begin because we are on a tight schedule. So, welcome back to the afternoon session. Those who are brave enough to be back will now get to see something different. So, I already put the slides for my first lecture on my webpage because, as I said, the slides contain vastly more material than I am actually speaking. Some of those are starred sections, but I just put them there for your reference, so feel free to check them out. Of course, they're making video, etc. for outside, but those of you who want to check out the slides at any point. And I was going to go through the theory of duality a little bit to talk about constrained optimization, but I decided that let's just dive straight into algorithms to try to put some of the knowledge that we have, or rather the vocabulary that we developed today morning, let's just try to put it to use for actual algorithms. These are the kinds that, okay, now you won't implement them, but you can still go and try implementing them in your favorite language to get a feel for how optimization works. And then tomorrow I will talk about the more, let's say, research edge of these things, about the kinds of algorithms that I'm talking about right now to make them work for large to very large optimization problems, which basically is all the interesting problems in machine learning. So, but there is a nice section on duality for that exists, which I encourage you to look at. And the highlight of that section is what I mentioned to you in words, that using that 0 belongs to the subdifferential type of Fermat's law to derive the KKT optimality conditions. And also, anytime you are solving an optimization problem, one of the main reasons you want to have access to optimality conditions is if you want to be really serious about deciding whether you should stop running your algorithm or not, amongst other things. Anyhow, so let's just actually talk about optimization algorithms. I'm going to talk about really simple optimization algorithms. These slides I have not yet uploaded. I'll upload them after the lecture. And okay, this is just a repetition. That link is alive, so you can actually click the PDF, but of course, you can search. And the first two references are my recommended books for you to go to in case you want to look at some of this theory from a textbook perspective beyond just lectures. Okay, cool. So let's talk about optimization algorithms. And as I kept on saying, first order, gradient based, subgradient based, let's just look at them. And just as usual, just to remind you why we are talking about optimization all the time. I talked about, the machine learning setting. So let's just say this is a simple supervised prediction setting. You're trying to learn a predictor parameterized by theta. Linear predictions like support vector machine logistic regression or neural networks. You learn a more complicated predictors, and this is the optimization problem. You may have seen this previously. This is, in fanciful language, the empirical risk minimization problem. So you have a cost loss function which says this is your predictor. It generated some prediction. Y is training data. Xi is training data. It's disagreement with the training data Y. You penalize it with the loss, and you want to minimize the loss. And to make the optimization problem nicer, we'll soon see what nice means. I'll try to quantify niceness. We may add some additional function there. And tomorrow I will focus on problems that look like that. Primary reason they are the standard empirical risk minimization problem. So I will talk mostly without showing you the explicit summation sign today, but you may keep at the back of your minds that whatever I'm talking about, ultimately, we want to care about algorithms that may take advantage of that you are working with gigantic amount of training data. So this N is a big number. Okay, standard example. maybe once you plug this in, then the example may also work. Of course, I will gradually accelerate, so bear with me a bit. Standard example, quadratic loss. So if L is the quadratic loss, you get a regression problem. If L is a logistic loss and Y is actually plus minus 1, not a real valued number, then you have a classification problem. And you can, H can be whatever, it can be classification within a neural network or what. So these are the two standard kind of examples. And now let's look at how to minimize these types of cost functions. And really there's nothing dramatic, pretty much pretty much obvious in some sense. The construction of the method, or like the desire to do this is obvious. How to do it is the non-obvious part. We're trying to minimize f of x for a long time, let's say since Cauchy's time in 1860s, when people were looking at first order optimization methods. So we are still looking at those. You start with this function, and if it's a convex function, you can even put a non-convex function in here if you want. What we try to do is that typically these functions, as you already saw for that logistic loss or something, you wish to satisfy that the gradient is equal to 0. That was necessary, and for convex problems also sufficient. So you wish to somehow construct a point at which the gradient disappears. And you could write the gradient equal to 0 as a bunch of nonlinear equations because you know what f looks like. Solving those nonlinear equations directly is really hard, typically impossible, and only in rare cases would you ever want to do that. And what we do instead is we start with a guess and we iteratively improve it until we reach close to a point where that condition is satisfied. As I said, this is the obvious kind of thing you'd want to do when you can't exactly construct the solution. Try to iteratively build it up. How to iteratively build it up is, of course, the whole story which comes up. So this is a standard generic descent method, and it's unconstrained optimization, so I can write gradient equal to 0. If it were constrained, we'll have something more fancy down. So let me show you a picture, one of my few pictures. So these are the contours of your cost function. Inside is better, lower cost, outside is higher cost. So think of topographic map, taking the iso contours. You're standing at x. You want to move towards the minimum inside. And this is the classical picture of gradient descent. There you draw a tangent. Doesn't look like perfectly perpendicular to the tangent. That's the direction in which the gradient of the cost function points. So these isobar lines are f of x values, okay, for different choices of x in the space. And you can see the negative gradient points inward towards the direction in which f decreases. And from this picture, you can see what you may want to do is you're starting at x. You want to move x in the direction of the negative gradient to move towards an optimum. There is a number there, alpha, which tells you how far along that direction do you want to move. If you move too far, if delta is like, if this number happens to be rather big, you may actually overshoot where you want it to go. So that's why this thing is called a step size, how far along you want to go. It's an important quantity. You don't want to overshoot, typically. Sometimes you can. You could say that, okay, I don't necessarily always have to use the full gradient. I could just use something that makes an obtuse angle with the gradient and just move in that direction. I will still end up decreasing the cost. So that's the generic strategy or differentiable optimization. And this strategy provably works if your cost function is convex. It sort of works somewhat provably if the cost function is non-convex. So this is the simplest way to try to minimize your cost function. There was a time in optimization around 90s. Lots of cool new theory came up. People started looking down upon this humble method. gradually, as problems became larger and larger in size, people started looking at simpler and simpler methods like this. And tomorrow I will talk about methods that are even simpler than this. But this is really what's happened. Okay? So this is your method, programmable in Python, MATLAB, whatever you wish. It's fairly obvious. Theoretically and practically, for anything to be called a well-qualified algorithm, it is important to have a stopping rule. Any infinite process, in mathematics, infinite processes can be called algorithms, but when you implement these things on computers, it's very important to figure out when to stop. And we're trying to reach a point where the gradient sort of is zero. Because this is finite precision, etc., etc., you will most likely never really reach a point where the gradient is exactly zero, so you have to come up with some tolerance. That's it. And you have to somehow guess, calculate, dream up, come up with theory, pick those two moving parts, which direction to go in, how much to go by, step size and direction, right? So here are some standard strategies. These are called, I'm calling them batch gradient methods. Some of you may know why. I'll expound upon that tomorrow. So classically, what people did for a long time, they tried to pick a good direction, which could be like the negative of the gradient, and they try to pick a step size, a positive number in the direction of the negative gradient, so that your cost decreases. It's a reasonable thing to think of. And if instead of the negative gradient you use some other direction vector, then it had better make that obtuse angle. So any vector that satisfies this condition, we call it a descent direction. So it's sort of like a gradient, but we didn't use the exact gradient for various reasons. And of course, nonlinear programming textbooks are full of different rules and techniques and procedures to select alpha, select B, and whatnot. That industry used to exist, now it doesn't. Sometimes you still need to think about these things, but it's good to be aware. And many of the batch methods, the standard batch methods, they were really insistent on ensuring that at each step they definitely make progress. So they were very rigid about being descent methods. And all the mathematical convergence theory, etc., hinged upon this fact. You can already, this foreshadows what you may already imagine. These days we are not so rigid. We don't always require monotonic descent. We'll soon see why. So here's just a quick summary. All sorts of things exist for descent directions. You may have heard of some of these names: Newton, quasi-Newton, whatnot method. Those are different strategies for picking a direction to descend. For it to be a valid descent method, you just have to prove that its inner product with the gradient is negative. So it sort of acts like a negative gradient. And you can come up with all sorts of choices. Diagonally scaled, fanciful versions of diagonally scaled gradient descent with some other bells and whistles go under the name of this Adam method that TensorFlow runs forever. So they're all coming from this simple structure, okay? And different choices of this lead to different complicated theoretical analysis. So, which is an understatement. For instance, this popular Adam method that people use, I don't know how many of you have seen that, but maybe you had the TensorFlow practical, you may have seen that already. We still don't know how to prove that it works. Okay, it works, but some people like to write the mathematical proof also to maybe gain some more insight and improve the method perhaps. So for the ordinary case with gradients, we know how to analyze, but if you use some of these more fancy things, without having access to convexity and full gradient, it's hard to analyze these things. But we use those methods for their empirical properties. And the research people kind of try to also prove the theory. Okay, so this is a short exercise for you. Should be able to work that out. And some of those other things, these are classical knowledge, like different choices of step size. And after that, this is my short introduction to nonlinear programming. Okay. What I'm saying right now, you kind of can choose all of these things also for non-convex. But keep in mind, theory we'll do for convex only. You can pick different types of step sizes. Some people like to use a constant step size. This is called the so-called learning rate parameter in machine learning language. It's just a step size for gradient descent, especially if it's a constant step size. Some people use non-constant step sizes. Some of those these are kind of very hard to get. That's like kind of get the best step size, which will make the best descent. Typically really hard to do, so we don't do it. Standard strategy. There's some other backtracking strategies for coming up with these descent rules. There's a very interesting step size strategy. This is the so-called diminishing scalar. So you don't use a constant step size. You use a step size alpha k, which is like 1 divided by k. So as k goes to infinity, the step size goes to 0. But the sum of all the step sizes, that diverges. And this is also a standard kind of step size used in so-called stochastic gradient method. Some of those we'll see tomorrow. And the crazy thing about these step sizes, they seem to help sometimes in practice. But with such step sizes, you can no longer guarantee that your cost is decreasing monotonically. It may even increase some point. Can happen. So we have to deal with that somehow. But because the step size goes to 0 in the limit, eventually things are going to be okay. That's roughly what it is. Okay, so those were like some standard strategies. And now let me just mention to you, when we start analyzing these, or when we start creating a mathematical model to solve a machine learning problem, some of the properties that we look at that play a crucial role in how well we can optimize, those start from these simple pictures. So this is like a smooth convex cost. This one is a non-smooth convex cost. We have a function f1, we have a function f2, and I define f to be the pointwise maximum between f1 and f2. f1 is a smooth function, f2 is a smooth function. The pointwise maxima of smooth functions can be non-smooth. It has this kink here, it's non-differentiable there. Fine. This is just to give a toy illustration of a non-smooth cost. There's nothing fancy about that. And one of the most standard class of cost functions you will see throughout machine learning is this class of differentiable costs that have a Lipschitz continuous gradient. It basically means that we are using, the reason this class was introduced, you can think of it this way. We are creating a gradient descent based method. And we want to follow the gradient or the negative gradient when making our updates. If the gradient fluctuates very wildly, then somehow it is not such a reliable quantity to use when doing updates. You may want to do very small updates because you're standing here, looks like gradient is a good thing, take a large step, you'll go down, but maybe the gradient fluctuates so wildly that if you take a large step, you may actually really damage the process. So people said, okay, let's try to look at a subclass of differentiable problems where we will only look at classes where the amount of fluctuation that your gradient can display from point to point is bounded. And that class is this Lipschitz continuous gradients. When you move from point x to y, the amount of change in the gradient is upper bounded by some fixed constant times how far you went. That's all. It's not only continuous, it is continuous with a quantifiable parameter and Lipschitz continuous. So these are called CL1 functions, C for continuous, once differentiable with constant path. So these are, whenever I say smooth, these are the functions we have in mind. Your logistic loss satisfies this, as does the square loss, and so on. Not all losses satisfy that property. Okay. So I told you why we look at that. And one cool thing is this lemma which quantifies for functions whose gradients don't fluctuate too crazily. This type of function can be upper bounded by just a quadratic function. And quadratic functions are slightly easier to minimize. We can even do a closed form minimization. So in some sense, you can think of gradient descent, which tries to go in the direction of the negative gradient, as the following procedure. At each point, you find the best, not the best, you find this quadratic upper bound on your cost. It's a quadratic upper bound. You differentiate it, you can set stuff to 0. You can explicitly minimize this upper bound. And to minimize that upper bound, you have to move from point x of k to x of k plus 1. That particular move will come by minimizing that upper bound, and that move is exactly the gradient descent update. So one way to think of the gradient descent update is repeatedly make these upper bounds, minimize the upper bound, make the next upper bound, and move on. This, in general, is a very valuable strategy, applies also to non-convex problems, as long as the gradient satisfies that problem. And this, in particular, is a very general strategy, which I don't know if Zubin in his lectures, if he talked about things like expectation propagation and expectation maximization as something. Those are essentially exploiting this type of strategy. You have a difficult cost function, find a simple lower bound if you want to maximize it, or find a simple upper bound if you want to minimize it, minimize the bound. Okay. That's a strategy. Gradient descent is one such strategy. Clearly not the only one. But the cool thing is, one can show, in fact, using a fairly short proof, I'm not going to show it, but it's somewhere in the slides, that if this function has a Lipschitz smooth gradient and it is convex, and it spits out the sequence using gradient descent with a fixed step size, then after k steps have been taken, you are guaranteed to be within a distance O of 1 by k of the optimum. So this thing is called the convergence rate. Gradient descent using this strategy at 1 by k convergence rate takes you close to the optimum. So just these things put together, they're making a really strong statement. So I'll mention for your benefit, this thing is called iteration complexity, because it says after you start from x0, you start from x1 in this case, you take k steps. After k steps, how close to the optimal value are you? There was a time in optimization in nonlinear programming where people used to always write theorems like lim k goes to infinity, then we can show some kind of speed of convergence. But when k didn't go to infinity, they didn't really know how to analyze. We implement these things on a computer, so it's good to have some insight into infinite number of iterations, how well are you solving the problem. And like I said, this property is good even for non-convex. Except in the non-convex case, we cannot make a statement about how close to f star have you reached after k steps. That's just, it sucks, but that's how it is. Okay, so that 1 by k convergence rate is also known as sublinear convergence rate in optimization, and which led people to think, are there some problems for which we can make gradient descent converge faster? So after k steps, can it come much closer to the optimum than what gradient descent did? And they saw that, okay, we were building gradient descent by always making this nice quadratic upper bound. And they found out that actually if you could sandwich the function between a tight upper bound and a tight quadratic lower bound, if you could always do that, then this function is morally only quadratic, and hence we should be able to optimize it quickly. That was the intuition. So there is indeed such a class. So previously mu was 0. If mu is 0, it's just convex. If it is bigger than at least a quadratic function, so mu is strictly positive, then it's called strongly convex. And strongly convex functions are functions which we can optimize faster than convex functions. In machine learning, they are important because often the regularizer that one uses lends strong convexity to the problem in the convex version of machine learning. And what it means in language of Hessians, I forgot the F here. So twice differentiable function is convex if and only if its Hessian has non-negative eigenvalues. And it's strongly convex if all the eigenvalues are at least mu. And what one can show, I'll write this theorem on the next slide again, that for strongly convex, you can use a fixed step size and in fact converge at what some people, we in optimization we call it linear rate. In linear algebra people call it maybe geometric or exponential rate. So don't let the terminology confuse you. Anytime somebody says method with exponential convergence, geometric convergence or linear convergence rate, they all mean the same thing here. This unfortunate use of terminology. So let's just say linear rate. And then, throughout optimization and machine learning for many years, there has been paper after paper of identifying problems for which you can get fast convergence rates like this. And even now you'll find papers at the NIPS conference, some of those will maybe show up this year also, that now we found a non-strongly convex problem for which we can actually converge at linear rate. That also happens. This class is just sufficient. It's not necessary for fast convergence. So if you discover a new class for which you can get fast convergence, which means this type of rate, you can write a paper, unless it's a boring class. So, okay, so this is the summary. For strongly convex, the gradient descent method, it will not only generate points that are close at this exponential rate, the f values are also close. And in machine learning, we typically care to make a statement about how far is your cost f from the optimal cost. We often ignore how far is the corresponding vector x from the optimal x star. If you want to study theory of generalization, you may wish to understand that. But from an optimization perspective, we think, okay, we spent so much effort building this mathematical model. So if it spits out xk or what, it generates some xk. We don't care so much, but what we want to ensure is that the model was good. So we typically care about that. Yeah. F star is the best value. Yeah. No. So the star, oh, sorry. This should be f of x star. Good typo catch, or let's call it notation abuse. And the convergence is determined by this quantity called the condition number. That language is borrowed from numerical analysis. It's just the ratio of between what kind of quadratics can you sandwich. So this is just the condition number, actually the condition bound on the condition number of the Hessian. So Lipschitz constant of gradient and strong convexity coefficient. And there's an entire industry, cottage industry called of optimization methods, where different people try to come up with methods which have weaker and weaker dependence on the condition number. So this one you can see there's a kappa in there. That's the dependence. So interestingly, this dependence on kappa, like I said, shows up in the analysis. And there was a theory developed in the late 70s which looked at these gradient style methods and shows that if your function is Lipschitz smooth, that means it's differentiable with Lipschitz constant L, then no matter how you combine those gradients, if you just use gradient based information, no matter if you use just the previous gradient, the gradient for past 1,000 steps or whatever, no matter how you use them, I can cook up a cost function for which gradient descent has to take at least O of 1 divided by k square steps. So I showed gradient descent takes O of 1 by k, and this says you have to take at least 1 by k square. And for strongly convex, you can cook up functions which take this number of steps. The previous method, gradient descent, depended as kappa, not as square root of kappa. So square root of kappa can be substantially smaller than kappa, right? So this led people to wonder, can we come up with something fancier than gradient descent, which actually attains these lower bounds? That was one of the most challenging open problems in the world of gradient descent methods until Yuri Nesterov solved it in 1983 by inventing Nesterov's optimal gradient methods. I'll only briefly comment on them. And to this date, people have not quite fully understood those methods. I mean, there are at least 10 published explanations of why they work, but still somehow, there's not a full understanding yet. But it's pretty cool that actually you can more cleverly work with gradients to attain the lower bound than just obvious batch gradient descent. And if anybody manages to have a really cool new understanding of these optimal gradient methods, which I'm not describing, I'm just telling you of their existence, that's going to be a valuable research contribution to both optimization and machine learning community. Okay, that was that. Now, that's why I put the star on that. The faster methods, these are Nesterov methods. I'm going to go rapidly through them, like really fast. But so these are also called optimal gradient methods, and they're called optimal because you have minimax matching of upper and lower bound. Somebody should be wondering, or many people should be wondering though, when I'm talking about lowers and upper bounds here, what kinds of lower and upper bounds are these? Many of you may be familiar with the notion of lower bounds and upper bounds from computer science. In computer science, we operate in Turing machine model. In optimization, we are working with real numbers, so we don't really operate in the Turing machine model. So when we talk about complexity here, this is a different kind of notion of complexity. This is called the oracle model of complexity. And the oracle model of complexity says, I want to minimize a function if I'm given access to f of x and gradient of f of x through a subroutine called an oracle. How many calls to this subroutine must I make to attain a specific accuracy? That's what the oracle model is. So yeah, within that oracle model. It's called the black box model because the oracle is viewed as a black box. Of course, you design the optimization problem. F of x is not a black box for you. You actually know quite a bit about what f of x looks like. So if you know what f of x looks like, these lower bounds may not apply to you. Okay? So it took, in hindsight, it's so simple, but again, it was in a formal paper, again, insight of Yuri Nesterov to realize this fact and to use it. Let's break the black box assumption, and you can beat the lower bounds. But just for your stoking your imagination. Okay, rapidly going through the past methods. This is just summarized there. So now back to our friends. To do gradient style stuff, but when things are no longer differentiable. Because I spent some bit of time telling you about the existence of subgradients and how awesome they are. In fact, for me, one of my favorite subjects within the world of convex optimization analysis is study of subgradients. So pretty much what I talked about for gradient descent, from an engineering standpoint, similar things you can do, even if instead of gradients you use subgradients. But in some sense, everything else kind of changes. So let's look at it. So this looks familiar. Rather than gradient, now we pick any subgradient. When this idea was put forth, this was, I think, put forth in the late 60s by Soviet researchers of that time, like a lot of stuff in optimization. And people thought, wow, that's kind of brazen. This thing is not even differentiable, and now you're plugging in this pseudo gradient-like thing in there. Will it work? And making it work was a nice achievement. And it turns out to be good and bad at the same time. So there are two choices, right? You pick some subgradient. There was once a time industry about trying to pick the best kind of subgradient, because there's an infinite number of those potentially, so you could somehow pick the best one. and prove theorems about it, and sometimes benefit from that numerically. The other choice is, as usual, how to pick a step size. And I'm calling it the subgradient method. I'm not, unlike gradient descent, I'm not calling it subgradient descent, because typically, you pick any old subgradient, it is not going to make you do descent in your cost. So that's why I'm not calling it a descent method. So of course, the questions you may want to ask, that if you try to run it with some subgradient, it will spit out some sequence. Does that sequence go to X star? Typically doesn't. Typically does not. But like I said, in machine learning, we don't care that much about getting X star. We care about F, right? So that's not too dramatic. So let's say, does it decrease F? Typically, doesn't monotonically decrease, but it sort of decreases it. That's the awesome thing. If you do a good job with the step size, the only other moving part in the system. So of course, then you may say, well, fine, it's not differentiable. You made me choose some kind of subgradient and some kind of step size. How fast does this procedure actually work? If it works, of course. So here is a toy example. You may have seen this so-called lasso problem, least squares with some kind of non-differentiable penalty. Here I'm computing so here, this is a subgradient. You can verify this is a subgradient using the rules of subgradient calculus from lecture 1. Should verify. And you plug that in with some step size. Kind of oscillates, but it seems to be decreasing the cost, right, as time passes. And if you are a little more careful about how you choose the step size, you can in fact even make it converge fast. It's still not going to be a strict descent method, but you can make it work better. So this was non-differentiable. We pretended to just run a gradient descent style method on it, and you could do it. And there's a sequence of different clever choices of the alphas to make this work better and better. That itself is pretty interesting. Anyhow, okay, so here are some choices for step sizes. This is a standard one that people use. So keep in mind, when I say step size for these methods that are not guaranteed to descend, so what is happening is these are non-differentiable functions. So essentially, just like the gradient can suddenly fluctuate dramatically from one point to the next. So they're not even differentiable, but you can think of them like the gradient being very fluctuating as an analog. So to tame these methods and use them in this gradient descent style, it's important to use small step sizes. That's roughly what's happening. So we often use this type of step size scale. And it's not a descent method, but you can keep a running tally of the best F value seen so far, and one can prove that after certain number of steps, the best F seen so far cannot be too far from the best possible F. So it's actually a reasonable method under that choice of step size. Again, valuable intuition at this point. Gradient descent allows you to use a constant step size. So if luck is on your side, which it will be if you design the F suitably, this statement means modulo, some small technical details is what it means. Gradient descent will decrease the cost by a fixed amount at each step. For example, if you had strong convexity in that case, or by a reasonably large decrease at each step. If that happens, then you can converge fast. Subgradient method uses a small step, so the amount of progress it really makes at one step cannot be much bigger than the size of the step size that you're taking, roughly speaking. So the speed of convergence of the subgradient method is kind of limited by that. If your cost function is awesome, then you can minimize it faster. So let me show you a toy. This is a toy exercise for you. If you've seen support vector machines, maybe you'll see when you see your introduction to RKHS world of things, I don't know. This is has been, and for medium-sized problems, you should always try an SVM. they still work very well. And there's a beautiful amount of mathematical theory they help bring into the world of machine learning. A lot of the SVM related stuff was done by Bernard's supervisor above me. So here you have a strongly convex regularizer and a non-differentiable loss. This is slightly different from loss plus non-differentiable regularizer, but whatever. It is strongly convex but non-differentiable. So it's non-differentiable, but you can still hit it with a subgradient method. You know from the calculus rule how to get a subgradient of that object. So you can essentially, if you manage to figure out a subgradient of that object, you can implement a solver to compute a support vector machine in 3 lines of MATLAB. You just got to figure out how to get a subgradient and you can do it. It's a good exercise to try doing that. And you can see that it actually also works, okay? And SVMs were responsible for actually establishing optimization as a major topic in machine learning. Because people wanted to solve this problem better and better and better, so people worked harder and harder on optimization. But you can still try the most humble method and see what happens. It's not too bad. Okay, so here is just an example of illustration of why we cannot be, even though subgradient method you could apply out of the box, why you cannot be too optimistic in general. So suppose your cost function is just the absolute value, single variable. So its minimum is easy, you know the minimum, right? It's just x equal to 0. But suppose you wanted to run an iterative method to minimize this cost function. It's a very trivial cost function. So you run a subgradient method. You know how to get subgradients of the absolute value function. That's just the sine of x, sinum. And absolute value of x is differentiable everywhere except at x equal to 0. Oops, that's the point we really care about. So you run subgradient method. So you initialize it poorly, and you pick some fancy step size. One can show that that is the best kind of step size to pick for it. And you run it. Then you plug that alpha in there, and you see that this is what xk looks like after k steps. So this shows that the speed at which you're going to 0 is just 1 divided by square root of k. So basically, you need to carry out 1 divided by square root k steps to get to get close to the optimum. Formally, it means that if you want the difference between f of xk and f of x star to be order epsilon, you'll need 1 divided by epsilon square iterations of the subgradient method to reach there. That's what this 1 by square root k translates into. Okay, so this may look like a kind of a cooked up example, right? But actually it's not really a cooked up example. This bad news of subgradient methods, it's bad because gradient descent was going at 1 by k. This is going at 1 by square root k, which is much slower. So 1 by k for gradient descent translates into O of 1 by epsilon. Epsilon is a small number, so 1 by epsilon is much better than 1 by epsilon square. Hence, this is actually bad news. And in general, with subgradient method, you cannot do better than that. There's a lower bound. You can see that in Nestrov's book. This is actually lower bound from Nemirovsky's book. That one can cook up a non-smooth function for which after k steps you cannot have done better than 1 by square root k. So the whole game turns into cooking up better functions f for which you can do better than converge faster. And numerically, these things can make a big difference. And some of you may say, oh, okay, you know, in neural networks, people use the ReLU activation. That is a non-differentiable function. It never bothered anybody there. Why care? But fine, that's one kind of standpoint. But if you want to understand something and improve them, it's good to care about this. In particular, I'll comment on that tomorrow about this ReLU stuff. So just saying that people build automatic differentiation and then they do differentiation willy-nilly, but oops, the ReLU function is not differentiable. Somebody should, not that it really mattered, but why it doesn't really matter. If you understand it, maybe then it's okay. So in some sense, you're allowed to violate the rules if you understand them. If you don't understand the rules, it's not good to violate. Anyhow, so this bad news can go away, and I'm going to show you that in a setup of some actual practical example. So we are trying to solve, let's say, constraint optimization problem. You could use that indicator function and then just try to hit it with subgradient method, but we don't want to be as slow as subgradient method. So what do? Well, we make assumptions. When faced with a wall like that, you make some nice assumptions which makes your day. So one of the assumptions is, let's assume, actually I overshot here. So just for simplicity, in fact, assume that f is differentiable, but you have constraints. So you could write f of x plus indicator and try to use subgradient method, but an interesting idea is that suppose f is differentiable, even though I don't write it explicitly on that next slide, and your constraints are simple. And I'll tautologically define what I mean by simple. So you run this iteration that instead of gradient descent, you use projected gradient descent. You could even use projected subgradient descent, but then in theory, projected subgradient is not going to be any faster than subgradient. So suppose the problem were differentiable, but you have some simple constraints. By simple, I mean I can solve this subproblem, orthogonal projection onto a set. If I can solve that subproblem quickly, whatever quickly means, basically in closed form or very quickly, then you can plug it in with subgradient method or with gradient descent method. And if your function happens to be differentiable, this method will converge as fast as gradient descent. Even though if you were to, instead of using the projection operation, if you were to put it up as an indicator function and use a subgradient method, it would converge slowly. By actually doing it with projections, you can converge faster. I'll speak about that once again. So this is a slightly artificial example, but you may try it out. So here I mixed the two things. I still kept a non-smooth thing up there. You can maybe ignore that if you want for now. Let's say lambda is 0. But you have some constraints like x is a non-negative number. So if you were to try to do subgradient method with that, it will be slow. But what you can do is just run the gradient style iterations. Let's put lambda equal to 0 to simplify it for you. And just solve this projection, which means truncate. If it's negative, just set it to 0. Otherwise, keep it as is. The max of 0, x function, right? That's it. You can run it, and this works as fast as gradient descent. So that's an instance of your. There are other settings where people have constraints like x should live between plus minus 1. That's an easy constraint. You can do that. And there's a bunch of other such simple constraints. And there's a collected body of literature that exists within machine learning, people collecting all sorts of easy constraint sets onto which you can project. And each time somebody discovers another easy set, they write a paper. Now, these days it's no longer so cool to do that, but at some point it was kind of cool, but not anymore. Okay, so like this one, if your constraint were a simplex, so if you're working with probability vectors, then x is a non-negative vector which adds up to 1. So it's a very important constraint set. Projection onto that constraint set can be done fast, which means if x is a vector of length n, you can actually project onto that constraint in O of n time, exactly n steps. That's really impressive. That particular subroutine has been rediscovered, not the O of n version, maybe the O of n log n version, has been rediscovered by at least, to my knowledge, more than 20 authors since 1940s to now. So that means there's at least 50 papers on that topic. So it's a very cool constraint. So anyhow, so let me just skip the remarks and actually show you. Well, there are a bunch of subgradient things I didn't cover. You know, there's all sorts of huge amount of research on subgradient methods, including these adaptive subgradients method like AdaGrad, Adam, etc. I'll remark on those later. But let me talk about this class of methods, which would be a pity if I didn't cover those in this class, is if now we have constraints, again, instead of using subgradient method with indicator function, let's try to do something more clever. So the moral of the story already is that, you know, if you know your constraint set a bit better, you know your cost function a bit better, don't just resort to the brute force of subgradients. You can often solve the problem better, and if you can, then why not? And so here is our friend, the optimality constraint back again, right? F is a convex function. If you have a convex set as a constraint, then for all x in that, the gradient had better form that angle. So you try to satisfy that necessary and sufficient condition for convex problems. If the problem is not convex, that condition is necessary, so you should anyways try to satisfy it. So it's a good condition to know about. So what you do, super simple. Instead of descending in an arbitrary direction, only go in directions which lead to descent. That was one idea. So, okay. So if X is a convex set, all the possible feasible directions take a very specific form. Let me show you a picture, actually, that will help you. So if it's a convex set, not every direction is a descent direction, but there are this bunch of directions which will lead to descent while remaining feasible. So again, you pick a distinguished set of directions that take you inside the constraint set. So you start with the constraint set and remain in the constraint set forever. And that leads to what is called a whole family of feasible descent methods. So there's the feasible descent versions of gradient descent, etc., etc. Let me tell you, one of the most popular feasible descent methods in machine learning currently is the so-called Frank-Wolf method. And I think then I'll have to stop, but I'll summarize for you. So Frank-Wolf methods are, let's say they're starting from this. This is our optimality condition, right? So if you're at a point where that condition holds for all zk in X, necessary and sufficient for optimality. So we try to satisfy that optimality condition. So if you're not at that point, that means there is still some descent left. You can still decrease the cost. So feasible direction, you can generate a direction in which descent happens. And what Frank-Wolf does is, it says, well, let's just directly try to minimize this. But this had better be non-negative, so you try to minimize this pleasure. So that gives you descent direction. You cook up a variety of methods to select alpha, and you make this update. You can rewrite this update in a more telling form. X of k plus 1 is 1 minus alpha into xk plus alpha into zk. So it's a convex combination of the previous solution and the new one that you just cooked up. And Frank-Wolf methods are really popular in machine learning because in many problems, this subroutine is easy to implement. You may see maybe tomorrow during Stephanie's lecture, there are some problems where the constraint set may even be exponentially large, that you may require an exponential length description to describe the constraint set, but you can sometimes solve this linear problem over that quickly. So that means you can even optimize sometimes really tricky looking constraint sets with this method. This method and its variants are popular in machine learning. Interestingly, just earlier, sometime late last year, is the first time where a more formal analysis of this Frank-Wolf scheme for non-convex methods was. So this theory holds for convex. Okay, so yeah, I will comment on some of that tomorrow because we've also looked at recently several versions of that. And I think there's one last idea I wanted to introduce to you, but we don't really have time left. So what I'm going to do is tell you the bottom line message again. And skip that part. Maybe I'll have to skip on that part. So what I want to tell you is just this particular message, that if you have a non-smooth problem, sometimes you can split up the non-smooth part to be separate from the smooth part. So you can decompose your problem into a smooth differentiable part plus a non-differentiable part. And there is a technique called proximal gradient method, which you should be aware of. And I derive it in a very intuitive manner in these notes in this lecture by purely doing the freshman style algebra on it. And if you can split your problem and exploit its structure, so this, you'll hear the word structure in machine learning all the time, but if you can exploit this property that it has a smooth part and a non-smooth part, then what you can do with the proximal gradient method is you can encapsulate the non-smoothness or the non-differentiability or the slowdowns that come from subgradient into something called a proximal operator, which is just a fancy way of doing projection. Okay, so think of it that way. In a way that your method still converges as fast as the full gradient method or Nesterov's fast gradient method. So that's the cool thing about doing this proximal part, banishing your difficult non-smoothness into a part that you can separate out and handle in a manner different from just raw subgradients. You can actually cook up a method that works much faster than subgradient methods. And these methods have been very influential, including in fields like compressed sensing. So unfortunately, I ran out of time, I think. Unless I'm mistaken, my time is up. So I couldn't describe to you the beautiful algebraic analogies that exist thanks to Fenchel conjugates between these proximal methods for handling non-smoothness and just plain linear algebra. But for some other day. So I think with that, I will just, let's see if I had any other final message to give you. I have, for your entertainment, I have put in a full convergence proof. It's good to go because that convergence proof gives you a convergence proof of gradient descent et al. As a byproduct. So just to mention the many other such fanciful methods of handling non-smooth stuff that I didn't cover, but worthy of knowing at least the names of, should you ever start having to develop or carefully implement these methods on your own. There is something called Douglas-Rachford splitting. A special case of Douglas-Rachford splitting in this method called ADMM, alternating direction method of multipliers, is kind of a special case of Douglas-Rachford. And there's a bunch of other methods, and studying some of these methods is, even in the case that I talked about, studying these methods, how fast they converge, making them work better on specific machine learning, image processing, signal processing, optimization problems is still a topic of research. But they're starting with just this underlying idea. Try to banish the non-smoothness into simpler part. So I think with that, I will have to stop. Thanks.
So in slides where you mention like all this steepest descent method, there you like D is identity matrix, that is way too fast.
So if you use the identity matrix, that is like doing gradient descent.
But that's like the step size is 1.
So okay, you sometimes put a step size before the D also. So you damp the D. Even when you implement a Newton method where D is inverse Hessian, to make it actually converge, you have to put a step size here. Until you reach the region of space where you can take big steps.
You said that we usually don't care whether the sequence generated by subgradient method converges to an optimal point. Can you give us an example when we do care if it is convergent to an optimal?
An example of where we would care. So it really depends on the application. So one thing that comes to my mind is if you're solving an optimization problem where these parameters represent some quantity that you wish to interpret, then you'd like to understand the result that came out. And once you understand the result that comes out, you may use that as feedback to go back and improve your mathematical model. Or sometimes when you are doing, like I said, generalization theory, trying to prove that doing empirical risk minimization is a good thing for minimizing the cost on unseen data, that time trying to understand the X that comes out may be very helpful for you. But usually trying to see the X that comes out is typically helpful when designing mathematical models worth optimizing. But in another case where you may care about that, and the reason is that suppose you cooked up some cost function. So let me give you a kind of toy example. So suppose you were doing some kind of image reconstruction problem. You have messy looking images and you want to make a sharp image. Then you may cook up some cost function and you may want to know, like for this cost function, the X star is like the best possible image that you can recover from it. And the X that you recover, is it really as good as that best possible or not? So when this X, the parameters have some physical meaning for you, then you do really care about getting them. But for subgradient methods, you typically cannot guarantee that you come anywhere close to X star. In fact, you can prove a theorem that even though you can reduce F, the xk generated by subgradient method remains a fixed amount away from the true X star. And I think it's only 2016 there was finally progress on trying to guarantee that you get close to X star when doing a subgradient style method, but you had to change the subgradient method to something fancier. So yeah, this is kind of a long answer, but if you care about interpreting your X, then you'd really like to guarantee that. Otherwise, still sometimes it's in many cases still open problem to even ensure that you get it. Question?